In this lab, we're looking into Newton's second law, which is shown here. This shows that the final velocity of an object can be found by looking at its initial velocity and adding the acceleration, which is just the total of all forces acting on the object divided by its mass. And then we multiply that in the change in time. So here we're concentrating on constant velocity, meaning that all the forces are balanced, so the acceleration is equal to 0. So using this, we should be able to look at the predicted motion of the ball with constant velocity against our observations in this video. Now in my video, I hit a pool ball across a pool table. I used the 7 ball in the background to calibrate it being 0.0381 meters in diameter. And then I chose to put the axes in the center of the ball that is moving. And that way it would move along the positive x-axis. And it's tilted slightly down just so it would follow the path of the ball during the video. Now during each frame you see I have found the center of mass of the ball during each frame. The frame duration being 0.05 seconds. So now with this data, we have our observed data over here on the bottom right corner. We have our initial position, and using the second position, we can determine the velocity of the ball. And to do that, we use this formula here, which is delta R over delta T, basically the difference of the 2 points divided by the difference of the time, which we have that plugged in here, and we get 0.7400 meters per second. So now that we have all the history of the motion of the ball that we need, we can use this code that would determine the position of the ball if it was in constant velocity. So we set the initial position, the velocity of the ball. We change, make sure delta T set to our frame duration, 0.05 seconds. And we're going to continue running this code while the time is 0.553 seconds or less. So now that we have our blue line here is the model data that we just received from the code, and you can see it's a straight line as you would expect with constant velocity. Although you look at the green line with our observed data and you see that it is actually slowing down. So some other forces had been acting on this ball. We have gravity pushing down and the table pushing up, which cancel out. We have our obvious hit to the right, and then in the opposite direction we have drag and friction. Now the drag is air resistance, which I don't think plays a major part in this in slowing it down, but as a pool table is made to produce a lot of friction. So the friction on the pool table against the ball caused it to slow down, which was why we see this difference in our graph. Now to do this experiment differently, to where the green line is closer to the blue, closer to constant velocity, we could have done this on a smoother surface with less friction.